Hello, everyone. Thanks for joining us today. So today it's our honor to have Joshua Sussan to talk about cellular algebra in categorification. Thank you, Joshua.
Okay, yeah, thank you to the organizers and everybody for being here. So this is joint work with Yu Chi. So I work in this field of representation theory, which intersects with low-dimensional topology, and specifically in this area of categorification. So maybe if there's time in the end, I'll say why I'm talking about cellular algebras. For the next, well, for most of this talk, I'm going to focus on something fairly algebraic, which has some combinatorial flavor, which is cellular algebras. So in the first section, I want to define what cellular algebras are. And I want to give some examples and why they're such a nice class of algebras. So first, definition. Okay. So let's let A be a finite dimensional algebra over some field K. And later on, I will want actually make the characteristic of K to be P, but there's no harm in just thinking of complex numbers for now. Okay. So cellular data for A consists of the following. One is first a finite poset, P with some ordering. Two, for each element in the poset, a finite set T of lambda. So for each element in the poset, we have associated a finite set. And then three, a function which goes over the Cartesian product of these finite sets to our algebra A, where an element S comma T, so S is in this finite set and T is in this finite set. This goes to an element CST lambda. Okay, and sorry, I'm learning how to use my pencil here. And so this is cellular data, and this data satisfies the following. So maybe the most important thing is that these elements CST lambda is a basis of our algebra A. Okay, so we have a very nice combinatorial enumeration of our basis. So it depends upon our finite poset, our element in our finite poset, and elements in the finite set associated to it. Two, and this is another crucial axiom. How does our basis interact with an action of an element A in our algebra, capital A? So this is a sum over basis elements CVT lambda with some coefficient, I'll say gamma SV of A in front, mod A greater than lambda. So just to kind of parse this out, when you act on some elements in your cellular basis, you get a sum of elements where this second index, Andrew, I think there's a question about my screen being shared. Everybody sees my screen? Okay.
I can see your screen.
You cannot?
I can
Okay.
see your screen.
Okay. And so, right, so we get a sum of basis elements, and we have these things in front of here are coefficients in our field. And the thing to note is that these coefficients, it depends upon this element S, it depends upon the element we're acting by, and it depends upon this output V, but it does not depend upon T. Okay, so that's a very crucial property of this cellular basis. And I'll, again, in a couple of minutes when I do examples, hopefully this will feel more natural. And then the third axiom is that the linear map, the linear map star from A to A, where a basis element CST lambda goes to CTS lambda. So this is not an algebra map. This is just a map of vector spaces where we're swapping the bottom two indices of our basis elements. But we're going to assume this extends to an algebra anti-automorphism. And this is, I mean, all these axioms are important, but I wouldn't worry too much about these. The one thing I want to say before I give an example, before I give examples, is that these axioms imply the following, which maybe is the best takeaway of this entire definition. These axioms imply that if I have a basis element Cij lambda and another cellular basis element Ckl lambda, this is equal to Cil of lambda mod higher terms. Again, there's an ordering on our post set, which gives some sort of ordering on our algebra, with some coefficient gamma here. But this coefficient gamma only depends on J and K. It doesn't depend upon I, and it doesn't depend upon L. And the example I'm about to talk about is just matrix algebras. And this is kind of how cellular algebras were thought of. It's a generalization of matrix algebras. Okay, and again, stop me if you have any questions. So maybe now it's time for a couple of key examples. So first example is, as I alluded to, we look at n by n matrices over our field K. It turns out that this could be made into a cellular algebra. Okay, so what's the cell data? So first of all, our finite post set just has one element. I'll just call it alpha. And then we associate a finite set for this element alpha. And I'll say this finite set is the first n natural numbers. Okay, and then I need a function. So I need a function which takes, well, here it's only, let me erase that. Because there's only one element in our post set, I need a function from T alpha cross T alpha into A. And so what is an element of T alpha? It's some element I. You could have another element J. This is supposed to go into some basis element Cij alpha. And what is this Cij alpha? It's just this matrix, which is 1 in the position ij and 0 elsewhere. Okay, and so a matrix algebra is a cellular algebra where we just take the unit, what do we call it? The standard basis for matrices is the cellular basis. And I should say the star of Eij is just Eji, so it's just transposition. So matrix algebras are an example of cellular algebra, but it's kind of a trivial example because the post set only has one element. Okay, so it's not really using the full power of matrix algebras. And of course, just to kind of highlight this property above, of course, we know Eij times Ekl is equal to delta Jk Eil. And so you see again, this multiplication of basis elements, it doesn't depend upon I, and this coefficient in front doesn't depend upon I and L. It only depends upon J and K. Okay, so that's this is a semi-simple algebra, and this is not so interesting. Although of course it comes up a lot throughout math. Another example is a truncated polynomial algebra. K bracket x mod x to the n. This is not semi-simple. And what is our post set for this? Our post set are the first n minus 1 or first n integers, non-negative integers. Okay, so now we have a post set with n elements with this standard normal ordering. And for each element in the post set, I need a finite set. And so Ti, I'm just going to say is equal to I, set I. Okay, and so then I need a function, C, which goes from the disjoint union, I goes from 0 to n minus 1 of Ti cross Ti into our algebra A. Well, each of these sets in this example only has an element I. And so what we end up mapping, so the function takes I comma I, okay, to some element Cii, But in this algebra, this truncated polynomial algebra, it just sends it to this monomial x to the I. Okay, and of course, so the most normal basis for truncated polynomial algebra becomes a cellular basis. And to see that this is to see just a couple of the most important property that this is really a cellular basis. If I multiply CII times CJJ, again, think this is x to the I and this is x to the j. Well, this is equal to delta I 0 CJJJ mod terms higher than j. Because, of course, x to the I times x to the j is x to the I plus j. If I is equal to 0, then 1 times x to the j is just x to the j. Otherwise, you get higher terms, but you ignore it. Okay, so it turns out that a truncated polynomial algebra is also a cellular algebra. Okay, so now so those are a couple of examples. Now to get back to some more important structures of cellular algebras, and then I'll get to a partial punchline. If lambda is an element in our poset, we could construct the following vector space, delta lambda. So this is the span of elements CS, where S are elements in the finite set associated to lambda. And this turns out to be delta lambda could be made into an A module as follows. So how does A act on CS? Well, it's supposed to be some linear combination of these vectors. And what you could do is you could look at how A acts on CST for any t. This is then some linear combination, as we said before, of CVT, and this gamma depends upon the element A, the element S, and the element V, but it does not depend upon T. And so then, since it doesn't depend upon T, I could then just rewrite this as sum gamma A, S, V, C, V. So these modules delta lambda, so delta lambda is called a cell module. Oh, and I should say mod A greater than lambda. Mod. Oh, yeah. There are some other terms, but you kind of think of these as garbage terms for the cell module, and you quotient out by them. Okay, so these are cell modules, which play a crucial role in the structure theory of cellular algebras. And the next ingredient is the fact that there's a bilinear form. It's a bilinear form on delta lambda. So that means that there's a map from delta lambda cross delta lambda into our ground field K. So what does it do? Well, if I take two basis elements, CS times CTB, if I multiply these together, well, we know from the remark much earlier that if I multiply these two things, I get kind of this matrix type multiplication mod higher terms with some coefficient in front. So I get, I'm going to leave some space for a coefficient, but I get lambda mod higher terms. And I have some coefficient here in front, which I called gamma earlier, but I'm going to now call this coefficient CSCT. Okay. And by the theory of cellular algebras, as I mentioned before, this thing doesn't depend upon A and B. And so this is how we define, so the pairing of CS and CT is defined as above. Okay, so one could prove nice properties about this bilinear form. And the most important next definition is the kernel of this bilinear form. So now I'll define the kernel of this bilinear form. It's all elements in our cell module, such that the pairing of V with W is equal to 0. It's like, yeah, it's the radical of any bilinear pairing you would have on a vector space for all W in W lambda. Okay, so that's a standard definition of a kernel of a bilinear pairing. And so then with this in mind, we define L lambda to be delta lambda modulo this kernel. And this quotient turns out to be L lambda turns out to be a simple module or 0. And so then we let P sub 0 be the set of all elements in our poset such that L lambda is not equal to 0. And now finally, kind of a major theorem in cellular algebras, which I think this theorem is due to Graham and Lehrer. I should have looked that up beforehand. So this goes back many, many years. All simple modules over A are of the form L lambda, where lambda is in this set P sub 0. And so this gives a classification of all irreducible modules over a cellular algebra. And that's where, in representation theory, that's a major goal is understanding all simple modules. Now, if I get handed a cellular algebra, it could be very difficult to figure out what this set P0 is. But for many important cases like Hecke algebras and what I'll talk about later, Webster algebras, this could be done with some work. Okay, maybe just to come back to the couple of examples before I move on to the major example that I'm interested in. So again, if we look at n by n matrices over our field K. Okay, so if I wanted to define the bilinear pair, well, first of all, there's only one element in our poset. So delta is spanned by Ci, where I goes from 1 to n. Because remember, for our example here, there's only one element of the poset, and the poset and the finite set associated to it has elements 1 through n. Okay, so how do I define multiplication here? So how do I define the bilinear form here? So first of all, I want to define, let me call this S, so things will be a little less confusing. Want to define the pairing of CS with CT. Well, by the recipe above, what I should do is I should multiply maybe CIS times CTJ. And remember, in the example of matrix algebras, CIS is just the matrix EIS. Okay, so this turns into, so this is EIS times ETJ, which is, of course, delta ST EIJ. And so this implies that the pairing of CS with CT is just delta ST. And that tells us that the kernel of the bilinear form is actually 0, because the pairing of any element with any basis vector with itself in the cell module is 1. So that means that nothing is in the kernel, which implies that the simple module is just the cell module. And this simple module is n-dimensional, and it's just the column vector. Okay, so in this example of a matrix algebra, cell modules are simple, and they are just column vectors. Okay, the other example for A equals this truncated polynomial algebra. Well, in this case, there's a cell module. Remember, so our post set goes from 0 through n-1. Okay, and our cell module only has one basis vector. It's spanned by x to the I as before. And now if we multiply c, so this was CII, and if I multiply CII times CII, this is some, I'll put the coefficient down in front in a second, mod A greater than I. Well, again, this is x to the I, and this is x to the I, and this is x to the I. Well, the only way that this survives is if I is 0. So this tells us that the pairing of xi, or maybe I should say the pairing of, the pairing of xi with xi is equal to 1 if I is equal to 0, and it's equal to 0 otherwise. And that tells us that the kernel of this is actually equal to the entire cell module. Well, maybe I'll write it like above. It's equal to 0 if I is equal to 0, and it's equal to the entire cell module if I is not equal to 0. And that tells us that L0, the simple associated to the post set element 0, is the cell module. And otherwise, Li is equal to 0 if I is not equal to 0. And so there's only one simple module, it turns out. So our post set, so our set P0 just has one element 0. Okay. And that corresponds to the fact that the truncated polynomial algebra only has one irreducible module. It has a lot of cell modules, but those cell modules are garbage in a certain sense. Okay, so that's kind of a background on cellular algebras. I now want to talk about the main example, which comes up a lot in my area of categorification of Webster algebras. So these were defined by Ben Webster about 15 years ago. And again, maybe at the end of this time, I'll explain why these are important. But these are nice or diagrammatically defined algebras. Okay, so first some words before I draw some pictures. So let's consider diagrams up to isotopy. Let's not worry about that too much. With red and black strands. I should say braid-like diagrams. I'll say what that means in a second. With red and black strands. Red from bottom to top. Okay, and I'll write a red strand as a squiggly thing and a black strand as a black thing too, so I don't have to toggle back and forth changing colors. And black strands, then I'll write an example. Black strands carry dots. Red strands can't cross. Okay, so an example of such a diagram might look something like this. That's a red strand, that's a black strand, that's a black strand. Black strands are allowed to cross, and I'll put a dot over here. And this could be, so you then look at the span of all such diagrams, And this could be made into an algebra where multiplication is given by concatenation. Multiplication is given by concatenation. So for example, maybe I'll have that picture here, and then I multiply it maybe by, make it a little more interesting. I multiply it by this. What I do is I stack the left picture on top of the right picture and I concatenate. So I'll put the right picture on the bottom. I'll put this kind of thing here just to know that I'm now gluing something on the top. What am I gluing on the top? I'm gluing this, this, this with the dot here. Okay, so there's a very natural multiplication where you just stack pictures. Okay, now this algebra has several relations, which I'll write down. These are important relations. These algebras have the following relations. First relation is if I have two black strands, if they have a double crossing, this is declared to be 0. I have this braid-like, if anybody's familiar with topology or Hecke algebras, or even symmetric group, I have this 3-strand relation where I can move one strand over this crossing. And I have this relation. So if I have a crossing with a dot on the top left or the bottom right, when I subtract, I get two straight black strands. Similarly, like this. These are so-called nil-Hecke relations, if you're familiar with the nil-Hecke algebra. So those are just relations having to do with black strands. What about when black strands and red strands interact? So if I have this red strand and I double cross it with a black strand, I could separate them. And the price to pay is I get a dot on this right strand. Dots flow through a red-black crossing. And I have this kind of other 3-strand relation where now 2 strands are black. Move this through there. That's a red strand. Plus reflections. I want plus reflections of these pictures. And then the final relation, or final 2 relations, is if I have a black-black crossing and I have a red strand cutting through like that, or I have a red strand cutting through like that, this straightens out in the following way. And then the final relation is that if I have a black strand to the left of everything else, this is declared to be 0. Okay, so these are all the relations. And just to give this some notation, if there are L red strands and N black strands, call this algebra WLN. So this is a Webster algebra with L red strands and N black strands. Okay, so this algebra turns out to have a cellular structure, and it has a nice combinatorial cellular structure, which I'm about to explain. Okay, so cellular structure on WLN. Okay, so first, so I need to define a poset. And the poset is a nice combinatorial gadget, which comes up all over in combinatorial representation theory. So let's consider Young diagrams. Lambda, and there's maybe a weird convention of how I read my partitions. So I have a partition with n parts, where I say the first part is at the bottom of the partition. Okay, which fit into an n by L minus n box. Okay, because again, this corresponds to the data of L red strands and N black strands. Okay, so as an example, if L is equal to 4 and N is equal to 2, we want partitions or Young diagrams which fit into a 2x2 box. And one such example could be this partition. So let's say here lambda 1 is 1 and lambda 2 is 2. Okay, and so there are 6 such partitions which fit into a 2x2 box. Okay, in general, it's just some common L choose n. Okay, so our post set is the set of such Young diagrams. Post set P is a set of such Young diagrams. And now for every element in the post set, sorry, this question from Fan is an n by 1 that's a column. Right. And so now, so our post set is a set of such Young diagrams. And for each element in the post set, we need a finite set. And this is what Webster calls a backdrop. So a backdrop S for our partition or Young diagram fitting into this box is an assignment, is a number assigned to each row, coming from, so what numbers can we assign to rows? They have to come from the labeling set 1 through L, the number of red strands. Such that the label, and I'll give you an example in a second, I know this is a lot of words, such that the label of the ith row from the bottom must be greater than or equal to I plus lambda I. Okay, and before I give some examples, I should say if two labels have the same row, if two rows have the same label, if two rows have the same label, use subscripts. All right, and I'll give you an example now. Okay, so again, let's take our example of lambda being this partition to 1 here. Okay, now for this first row, lambda 1 is 1, and it's the first row. So whatever I assign here, it has to be bigger than 1 plus 1, which is 2. For the second row, this is row 2, and lambda 2 is 2. So whatever label I put here has got to be bigger than or equal to 4. Okay, but again, we're labeling things through 1 through 4 because L is equal to 4. So that means that the top row had better be labeled by 4. Okay, and so let's there's a lot of possibilities, but here's one such possibility. I could label this bottom row 4. I have to label the top row 4. And now, since I have two things with the same label, I better use subscripts. So I'll put this 1 here. I'll put a 2 here. But I could have also said this is 4, 2, and this is 4, 1. Okay, I want to concentrate on these two, but there's many others. Another example could be, this could be 4, and this could be 2. Many other things. Okay, sorry, I don't know if I'm going too fast, but are there any questions about, maybe it's too hard to digest all of these things carefully, but these are so-called backdrops. And now, what do these have to do with Webster algebras? Well, I now want to assign diagrams for these backdrops. Want to assign diagrams to these backdrops.
Wait, sorry, I have a question.
Yeah.
Here it says it's bigger than or equal to I plus lambda 1. So,
Lambda I.
I plus lambda I, right, sorry. So for the first row from the bottom, so the bottom row, that should be bigger than or equal to 1 plus lambda 1?
Yeah, and lambda 1, this is lambda 1. The bottom row is lambda 1.
Oh, lambda, oh.
It's whatever, like I don't know if this is French convention or some other convention. Lambda 1 is the bottom row and lambda 2 is the top row.
I see, okay, thank you.
Okay. Okay, so we want to assign diagrams to these backdrops. So for the bottom of a diagram, and after I write these words, I'll do the examples above. For bottom of diagram, we have a black strand directly to right of red strand. For top of diagram, in between I and I plus first red strands, the number of black strands is the number of rows labeled I, okay, and then connect. Okay, so there's a lot of words going on here, but I think these examples will help quite a bit. So let's, maybe ignore those words. So let's look at a running example. Here's 4-1 and here's 4-2. Okay, so how do we construct, so let me move that over a little bit. Let me call this backdrop S. This is 4-1. This is 4-2. And then I'm going to associate a diagram, which I'll call BS. Okay, so on the bottom, I need a black strand immediately to the right of the I plus lambda I red strand. Okay, so here, here, this is 1 plus lambda 1 is 2. So I need a black strand directly to the right of the second red strand. So I have 1 red strand, 2 black strands, sorry, 2 red strands, black strand. Here I have 2 plus lambda 2 is 4. So I now need a black strand to the right of the fourth red strand. So I write third red strand, fourth red strand, and then a black strand. Okay, so that's the bottom of our diagram. Okay, then at the top, I need a black strand in between the I and I plus first red strands. How many of them? Well, it's given by the number of rows. So in between the first and the second red strands, there's no row labeled by 1, so there's no black strand there. Between the second and third red strands, there's no row labeled 3, so there's no row labeled 2, so there's nothing there. In between the third and the fourth red strands, there's no row labeled by 3, so I don't put a black strand there. That must mean that I have 2 black strands to the right, and now I connect. And first of all, let's just connect the red strands. And it turns out that you have to prove some things, that the connecting is independent due to relations in the algebra. The only question is, how do I connect this black strand up here? Well, since this is a 1, the subscript is 1, I connect it to the first guy. How do I connect this thing here? Since the subscript is 2, I just connect it up there like that. So that's the diagram associated to S. What about to the diagram T? This is 4-2, and this is 4-1. Okay, so the bottom is the same. Red, red, black, red, black. The top is also the same because there's just 2 4s. Black, black. But now how I connect, because this is a 2, I connect this to the second black eye. connect this to the first, oop, that should be strip black. I connect this to the first black guy, and then I just draw my red strands in there. And we have our diagram. Okay, and now getting closer to a punchline. So now I could define an element CST lambda in our Webster algebra. This is given by BS. I just told you how to define BS. BT star. What does BT star mean? It means flip BT in a horizontal axis. Okay, and now a theorem of Webster and Stroppel and Webster. Is that these elements CST lambda is a cellular basis of our Webster algebra WLN. Okay, and one more theorem in the section, and then I'll try to summarize what Chiu and I did. This is a theorem of Webster. So it turns out that the number of simple objects, simple representations of WLN is L choose N. Okay, it's really given by the number of each cell has a unique irreducible representation. And remember, for an n by an n by L minus n box, there's L choose N elements in our post set. Okay, so we have a nice classification of the irreducible representations of this Webster algebra. And from a categorification perspective, which I didn't have time to, well, I don't have time to talk about what this categorification program is. So this is part one of the theorem. Part two of the theorem is that if you look at the direct sum, n goes from 0 to L, of the category of modules of this Webster algebra, and look at their Grothendieck groups. Well, the Grothendieck group is a vector space spanned by the number of simple objects. So each piece here, the Grothendieck group, is a L choose N dimensional vector space. But it turns out that there's actually a lot more structure here. And it turns out this is isomorphic to V1 tensor L, where this is a two-dimensional representation of the quantum group UQSL2. So I'm not going to, the algebra is quasi-hereditary. So I didn't have a chance to define what UQSL2 is. It's a deformation of the enveloping algebra of SL2. V1 is the natural two-dimensional vector representation, and then taking the L tensor product. And so this turns out to be not just a vector space, but a representation of UQSL2. And so just to say, so this gives a categorification of V1 tensor L. Okay, so I have a bunch of categories whose Grothendieck group is this other representation theoretic structure. Okay, and maybe I'll just say very briefly what Chiu and I did, but not go into any details because this is already getting too into the weeds. So theorem of Chi and myself is that WLN has a PDG structure, So a DG algebra is an algebra with a differential, with a derivation which squares to 0. A PDG algebra is an algebra with a derivation whose pth power is equal to 0. And if you look at the direct sum of these categories, WLN, with this PDG structure, which I'll call D. You have to look at the derived category. This is isomorphic to, again, V1 tensor L, but as UQSL2 representations, where this is the small quantum group. Okay. So sorry, this theorem is, I just really rushed this because I'm running out of time. And I think for the last couple of minutes, I just want to give a broader perspective on the categorification program to give a place for all these algebras, why we study these algebras. Okay, and so maybe just for the last couple of minutes, overview of categorification program. So we have some motivation for all these things. So this is a program introduced by Crane and Frenkel probably about 30 years ago. So for a link L, there's something called the Jones polynomial of link L. And it turns out, so this is a polynomial which depends upon a parameter Q. If I take Q to be a root of unity, then this Jones polynomial could be made into a 3-manifold invariant, where M is given M is a 3-manifold, which you get by doing surgery on some link L. Okay, so this was work in the early 90s of Witten coming from a physical perspective and Reshetikhin and Tarayev coming from quantum groups algebraic perspective. Okay. Then Havanov categorified the Jones polynomial. So this is Sarah of categorification. This is called Havanov homology. This is a homology theory of links whose graded Euler characteristic is the Jones polynomial. Okay, so this is a more powerful link invariant. And so then the big question in categorification is, could I get this is a big question mark, could we get a categorification of this 3-manifold invariant? And what you need to do is, so this Jones polynomial comes from the representation theory of UQSL2. And so you need to categorify the representation theory of UQSL2, which was done by Havanov, Lauda, and Ruquier. But then the question is, could you categorify the representation theory of UQSL2 at roots of unity in order to go in this horizontal direction? And so this uses PDG structures and categorification. So I would view this theorem of Chiyu and myself as one very small step in trying to construct a categorified 3-manifold invariant, which would ultimately lead to 4-manifold invariants. Now, I know that subject is, this is very far away from combinatorics, but in this big program to get powerful topological invariants, we need to understand representation theory of some very combinatorial algebras which have these cellular structures. Okay, so maybe this is a good place to stop. Thank you for coming.
Thanks very much for your talk. Are there any questions?